Welcome back. We're on part 3 of physics of the atom, and now we're going to deal with radioactive emissions. Now, some elements emit ionization energy all the time, and they're referred to as radioactive elements. Now, the definition of ionization energy is the quantity of energy that an isolated atom in a gaseous state at the ground level, ground electronic state, would absorb so as to discharge an electron, and what the result of this is a positive particle or cation. Right? So this energy is usually measured in kilojoules per mole, which is the amount of energy it takes for all the atoms in a mole to lose one electron each. And you remember, I hope you remember that the quantity mole is one of the basic quantities that we would have studied from, I think, chapter 2 or 3. Now, radioactive elements are naturally found in the environment, in the soil basically, and they emit background radiation. Examples of radioactive elements are shown. You can see uranium. Uranium is a hot one. Everybody always talks about uranium. Thorium, iridium, so because of this, these things, these pictures you see here, these elements, which are usually found just like this in the soil, deep down in the soil. People who are miners that dig in the soil and stuff, they are subject to background radiation, so they have to be very careful with how they approach the digging process and what clothes they wear and the safety materials they all use, right? Now, some pioneers of radioactive elements are of discovering them, noticing how these elements work. Henry Becquerel, Marie Curie, and Pierre Curie. So in 1896, Henry Becquerel noticed that after leaving a sample containing uranium in a drawer near some photographic film, the film became exposed. He theorized that the uranium was producing invisible rays, which caused a chemical reaction in the film. Over the next few years, there was Marie and Pierre who investigated other minerals. This is what we call the rocks, the little rocks, as we saw on the other slide. And they isolated radium in sufficient amounts to study its properties. There is always some amount of background radiation around us. And the question asks, where do you think it comes from? Of course, it comes from the soil, it comes from outer space, from the sun. So all of these things, we are exposed to radiation all the time. However, the levels are very low in terms of in normal spaces. However, if you put yourself in a position to be in direct contact with radiation, you can suffer from cancer specific to whatever radiation you would have exposed yourself to. Okay? Now, investigating nuclear radiation. There are 3 types of nuclear radiation that we know of. You have the alpha, you have beta, and you have gamma. Alpha particles are positively charged and they don't penetrate as deeply as the other 2. However, they're easily absorbed. Beta particles are negatively charged. They penetrate more than alpha particles but less than gamma particles. And gamma rays are the strongest ones. They have no charge whatsoever. They penetrate materials the best and are the least absorbed of the 3 types of particles mentioned. A Geiger-Müller tube is used to detect ionizing radiation. A radioactive particle passing through a Geiger-Müller tube produces an electrical pulse, which is logged by a counter attached to the tube. And once you put the Geiger-Müller tube in front of whatever source, it will pick this up and the penetrating power will be investigated from that. When a radiating source is placed in front in a magnetic field, only two particles would deviate from its normal path, and those particles would be alpha and beta, because one is positively charged and one is negatively charged, so they're affected by the magnetic field. However, gamma rays are not. The same thing whenever you place a radiating source in an electric field, right? Only the alpha and the beta particles will be affected. However, gamma is not, because it doesn't have a charge. Okay? So as you can see there, the one with the greatest deflection is beta, and the one with the second greatest deflection, which is not so much as beta, is alpha, and the one that doesn't deflect at all is gamma. So gamma is basically unaffected. And now I have a table here that simplifies what we would have learned. So with alpha particles, the nature is that a particle consisting of 2 protons and 2 neutrons is ejected from the nucleus. The electric charge carries a positive 2. Penetrating power is not so strong. It can be blocked by paper or skin, and it's strongly ionizing as it is massive and highly charged. It deflects the magnetic and electric fields, deflects the alpha particle. With beta particles, they are fast moving electrons ejected from the nucleus. It has a -1 charge, can travel a few meters in air. However, it can be blocked by metal foil. It's ionizing. It's in between alpha and gamma, and it is also deflected by a magnetic and an electric field. With gamma rays, the radiation is emitted by the nucleus, and it's a high energy photon. It doesn't have a charge. It can travel very long distances, and it has quite a lot of intensity, in that it can penetrate a lot of thickness of lead or metal before it's stopped. It has some ionization, not too much, and it is not affected by any magnetic or electrical field. So here we have comprehension. Why would these carriers possibly lead to you having a higher than average annual dose of radiation? So a radiographer in a hospital, airline pilot, and a miner. Then we have question 2, what types of nuclear radiation can penetrate your skin? B, causes the most ionization. C, are deflected by a magnetic field. And D, can travel the farthest in air. So let's try to answer these. You can pause the video and then come back. Great, so you're back. So now, why would these carriers lead to you having a higher than average annual dose of radiation? A radiographer, first, you might have to look up to see what a radiographer is. A radiographer is the person that takes the X-ray, right? So they're exposed to X-rays, right? These persons are exposed to X-rays daily. Airline pilots, they're in direct contact with the sun once they're flying during the daytime. And with miners, they're basically going deep into the soil, and they're in direct contact with radioactive minerals. So because they work in soil, deep below the surface, they are in direct contact with radioactive minerals. It says, what types of nuclear radiation can penetrate your skin? We know that's no, not alpha. What types? Beta. Will be beta and gamma. Causes the most ionization. The most ionization would be gamma. Let's make sure. Sorry, alpha. My bad. So it will be alpha. My bad. So we have here alpha and are deflected by a magnetic field, so it will be alpha, and beta can travel the farthest in air, that will be gamma. So I hope this helped you. See you around for part 4. Okay, so nuclear decays and radiation and reactions. Welcome back to physics of the atom. Welcome back to physics of the atom part 4, and we are now going to look at nuclear decays and reactions. So many nuclides are stable, and it simply means that the nucleus has the correct balance of protons and neutrons, and then it therefore doesn't have to break apart. However, some nuclides have too many neutrons or too many protons, and this makes them unstable, causing the nucleus to decay or break apart over time. For example, carbon-12 is a stable nuclide, but carbon-14 is not. Carbon-14 nuclei will decay over time, changing into nitrogen-14 nuclei. When a decay occurs, it can be described in these simple terms. You have the parent nucleus, you have the daughter nucleus, and then the alpha, beta, or gamma radiation. Okay, so the parent nucleus, once it breaks apart, will form a daughter nucleus, meaning it was born from that parent nucleus, and then you would have, depending on the parent nucleus, you would have whichever radiation that's specific to that parent nucleus, type of radiation. So alpha decay, the general form of an alpha decay equation is such that whenever the parent nucleus breaks down, you would have a helium coming off. Alpha particles are basically helium particles, right? And so this would be the emission. This should be the alpha emission, and then this will be the daughter. So when you get the daughter nuclei, the mass number will decrease by 4, and so would the atomic number. Okay? Now during alpha decay, an unstable parent nucleus releases 2 protons and 2 neutrons bound together, forming an alpha particle. The alpha particle is ejected from the parent nucleus, leaving a daughter nucleus with less mass. And as 2 protons have left the nucleus, the resulting daughter is a different element than the parent. With beta decay, we have the emission of an electron. And so the daughter nucleus would have the same mass as the parent. However, its proton number would increase by 1. So a beta particle is a fast-moving electron produced when a neutron converts to a proton inside of the nucleus. The electron was not originally present. After decay, there is an additional proton in the nucleus, and so the daughter nuclide is a different element from the parent. With gamma decay, you have no change at all happening. The parent nucleus is the same as the daughter nucleus. So an alpha or beta decay may leave the daughter nucleus with some excess energy. The nucleus is said to be in an excited state, and this energy may be released by a gamma decay. Gamma decay does not cause any change in the number of protons or neutrons in the nucleus, and so the product of the decay is the same element as the parent nuclei. Large nuclei can split into smaller nuclei, releasing energy, and this process is usually caused by hitting the nucleus with a neutron in induced fission. The neutron is absorbed, and then the nucleus becomes so unstable that it splits up, and during fission several neutrons are released alongside the two new nuclei. In nuclear reactors, these neutrons are used to cause further fissions and form a chain reaction. Nuclear fusion, though, but it's the difference between nuclear fission is great in producing energy, and that is what some countries use to produce electricity in their country, because they only need a small amount of uranium to produce a large amount of energy. However, the byproducts are not good for the environment, right? So that's the only downside to this. Nuclear fusion, on the other hand, is a cleaner way to produce a lot more energy, because the byproduct is a gas which is inert, it's helium, and it doesn't pose a threat to the environment. I don't think it will cause global warming either, right? So stars produce their energy using the process of nuclear fusion. In this process, small nuclei are merged together to form larger ones, and the sun produces all of its energy by nuclear fusion processes, mostly fusing isotopes of hydrogen to form helium isotopes. And we have this example right here, and I think you need to learn it, because you never know when it's going to come. So it says here, comprehension, write complete decay equations for the following. It says the alpha decay of americium 241 into an isotope of neptunium. So if we have americium 24195, it says alpha decay. So we know that alpha decay is a helium particle, 42, and then therefore we have this at MP, and we just minus 4 from 241, so that would be 240 minus 237, and then this would be 95 minus 2 would be 93. So that's your new element right there, your isotope. The beta decay of cesium 13755 into an isotope of barium. So we're going from 13755 and releasing an electron. So 0, -1. Plus, remember, the mass number stays the same. However, this -1, you would add it because remember, you're creating something inside of the nucleus. So you're going to have 56, and it's barium right here. It tells us. So all we had to do was work out the mass number and the proton number. And if you go back, you would see, let's look at the table. What did it say in the table? It says, is it there? Electromagnetic radiation, fast moving electron ejected from nucleus. No, so yes, so beta decay says a beta particle is a fast moving electron produced when a neutron converts to a proton inside of the nucleus. The electron was not originally present. So after decay, there's an additional proton in the nucleus, and so the daughter nuclide is a different element from the parent. So we see that there's some change inside of the nucleus. So we know that it went from 55 to 56, therefore changing from the parent to a different daughter nucleus. And it says, what is the decay equation for alpha decay of polonium 220 into an isotope of lead? So alpha decay, lead 206, 82, alpha decay. So we're going to minus 4 from 206, which is going to be 202. And 2 from 82 will leave us with 80. And the tallest is, polonium. So I went wrong there for a minute. This is what happens when you get excited about physics. Are you excited? Right, so the one is the decay equation of alpha. Oh, my bad. Oh, I was so excited just now that I didn't even realize what I did. So let me rub this out. So let's do this again. So we're starting off with polonium 210. So we want to find that. And we're going to the, so it was backwards. So something you have to be careful when you read the questions. I just got a little hype. So we went from 210 to 206, so we minus 4 from 210. But since we're going backwards here, we're going to have to add 2. Because we had to minus 2 to get 82. So we're going to add 2 and we get 84. Okay? And I think that's it for the comprehension of this topic. See you soon for part, I forgot the number, but see you soon for the next part. Bye! So, right, so 197 minus 79 will give you 118. Oh, yes, so 118. And then now we have osmium, so we have the number of protons. So you could just put it back on the electrons. And then you want to know the nucleon number. You just add the protons plus the neutrons. So 76 plus 114 will be equal to 190. So 190. I hope you got these answers. See you around for the next installment of part 3 of physics of the atom. Bye.